Hi, this is section 3.2, naming ionic compounds. So as a review, section 3.1, we talked about how to name molecular or covalent compounds. And today we're going to learn how to name the ionic compounds. So molecular compounds were discrete molecules with exact numbers of different atoms in the molecule. So, for example, the glucose listed down here at the bottom has exactly 6 carbons, 12 hydrogens, and 6 oxygens in each one of the molecules. They're non-metal atoms covalently bonded to each other. And every molecule is the same. All glucose molecules have the same number of atoms of each kind, and so on. But the ionic compounds are not composed of molecules. They're extensive arrays of ions, just stacks and stacks. And the one above it and below it and beside it, they're equally bonded to all the different ions in all the different directions. So, and then they're metal ions bonded to non-metal ions. And they don't go, their name is not according to any kind of molecule. It's just the simplest ratio of each kind of atom that's in the array. So it's known as its formula unit. So sodium chloride is its classic example. Now, on this next slide is a little bit different kind of periodic chart than what we've looked at so far. This one tells the ions or the charged atoms that that all the atoms on the periodic chart likes to make. So we have our group 1 elements on the periodic chart. They're known as the alkali metals. They have 1 electron that they like to lose when they bond to things, and that makes it have an ion with a +1 charge. So the cations are on the left-hand side, and the anions are on the right-hand side. The second group, group 2, are known as the alkaline earth metals, and they have 2 electrons that they will easily lose. And so they have a +2 charge when they form an ion. Group 3 metals have a +3 charge when they're a cation. Group 4 elements are usually, especially carbon and silicon, they don't usually form ionic bonds at all. They only make covalent bonds. So I didn't highlight group 4, although down towards the bottom, germanium, tin, and lead do, but they've got different charges. So group 5 starts our anion groups. They like to gain 3 electrons, so that gives them a -3 charge. So we have nitrogen, phosphorus, and arsenic. Then group 6 likes to gain 2 electrons. Then we have the purple group, the halogens, and they like to gain 1 electron. So they have a -1 charge. The noble gases, of course, don't like to gain or lose electrons. They don't like to react at all. So that's why the little red crossbar thing is there. If you notice, I highlighted hydrogen. So hydrogen, normally we're used to seeing it at the top of group 1, but I also copied it over here and put it in group 7 for the top of the halogens. Now it's not a halogen, but it does like to gain an electron, and it only has 1 electron normally, but when it gains 2 electrons, it's more like helium. So sometimes it likes to gain an electron, sometimes it likes to lose an electron. So it can be either way. So that's why it's on both sides. Now, remember that cations are the positive ions. They have more protons than they do electrons. And anions are the negative ions. They have more electrons than they do protons. So these are the negative, the anions, and this side is the positive. Now these down here are more complicated, so we'll talk about them on the next page. But we're going to talk about the simple cations, the positive, and the simple anions, the negative ones, on this page. So some good examples are highlighted in green. So calcium right here in group 2 has a 2+ charge. Cesium over here in group 1 has a +1 charge. And then in the anion section, we've got phosphorus with a 3- charge and bromine with a -1 charge. Okay. Now, these are not as simple. If you notice some of the ones in purple here, they have 2 different charges. So there's lots of them that can have more than, they like to form more than one type of ion. So here's some examples. So there's a new system, a newer system called the stock system, where it tells you which one they're talking about by using Roman numerals. So here we've got chromium. If we look at chromium right here, we see it can make a 2+ ion or it can make a 3+ ion. So unless it says, it's kind of hard to tell. So here they put chromium with a Roman numeral 3, and so we know that it has a 3, it's the 3+ ion. Then also copper, it can have a +1 or a 2+. So here it's got the Roman numeral 2, so automatically we know that they're talking about copper with a 2+ charge. Iron right here can have a 2+ or 3+. So here's iron with a 2, Roman numeral 2, so 2+. And then lead can have a 2+ or a 4+. So lead with the Roman numeral 4, so 4+. Now mercury's really weird. So mercury can have, actually it says it's a 1+, which it is, but the trick is when it's always diatomic when it's 1+. So that makes it 2+ because there's 2 of them. So 2 1+s together. See that subscript? See the subscript right there. So Hg2. So it's diatomic. There's 2 of them, and each of them have a 1+. So a total of 2+s. So it always appears with the subscript and the superscript. So that one's a weird one. Now notice there's no anions. They don't mark them with the Roman numerals for anions. They just have the 1 charge when they're negative. So it's just the cations that can have, and they're the transition metals mainly that do these different charges. So now they do the stock system now, but you'll still see remnants of this older naming system, and it was confusing, and that's why they changed it. So here is this chart in your book, table 3.3, and you can use it like to interpret between the two, because it's difficult to keep track unless you just used it all the time. It's hard to keep them straight. So the pattern that they did was that whatever ion, so let's look at cobalt here. So cobalt can make a 2+ or a 3+ ion. So the smaller of the two, they used to put the OUS ending on it. So it was cobaltous ion. And then the one that was larger, they put an IC-ic ending on the word. So cobaltic ion and cobaltous ion. The same with copper here. So the smaller one has a 1 plus charge, and the bigger one has a 2 plus charge. So cuprous and cupric. So this one had 2 and 3, and this one has 1 and 2. So I mean, and it's hard to remember, unless you're a chemist, whether copper will make twos and threes or ones. So with the stock system, there's no having to memorize things, it's just right there. But I would keep this table 3.3 handy, or just to refer back and forth if you need to look up anything that ends in OUS or IC. So they're all positive ions, and whichever one is the smaller of the two has the us ending, and the bigger one has the ic ending. So there's a lot more besides these elements, or, well, no, I think that's actually most all of them. I'm thinking of something else. All right, now on the front of your lab binder, there's a laminated periodic table of the elements, and the box on the bottom right-hand corner has a lot of these same ions. So that's a great chart. And if you flip it over, there's more charts. Um, this one that I've got here on this page right here is really good. I'm not sure what's better, but I made copies of this and gave it to you later, so you should have it before today. It's the new paper that's in the little plastic sleeve. So for everything that I go over in this lecture, this chart will work great. So, but you could possibly, if you don't see it on this chart, you can look on the back of the laminated sheet that's in your lab binder. So first of all, polyatomic ions are just like what the name suggests. It's more than one atom that has a charge. So it's a group of two or more atoms that these are covalently bonded together, and they carry a net electric charge, either positive or negative. So they form, with the exception of one of them, they're all negative. Over here in the bottom right-hand corner is the ammonium ion, NH4, and it's the only one on this chart that has a positive charge. So see, it's +1. All the rest of them are negative. So this box and all the orange ones have a -1 charge. Then the next group has a -2 charge. The pink, or whatever color this is, has a -2 charge. And then this yellowish color is -3 charge. So they travel as a group. So they're covalently bound together, but they stick together as a team, and they travel together and bind to other ions. So if there's only one, you probably won't see a parenthesis around the polyatomic ion. But if there's more than one, you'll always see it enclosed in parenthesis and then a subscript showing how many of them that there are to balance the charge. All right, so you'll understand better what I just said now. This is the formula for naming ionic compounds. So if there's only one possible charge, use the element name. So the cation goes first, and then the anion. So this is the metal side. So if it's just one, if it only has one possible charge, use the element name. If more than one possible charge, so some of the or a lot of the transition metals, some group 13 through 15, so that's group 3, 4, and 5 as well. Write the element name, including the charge, in Roman numerals in parentheses. Then on the anion part, if the compound is binary, so that means if there's just two elements altogether, the cation and then the element for the anion, just change the ending to "ide." But if it's a polyatomic anion, then you use the name from the chart that we just looked at. Okay, now I know that was confusing, but I think it'll make more sense once we start doing it. Okay, so here's some examples. So we have strontium chloride. So this was the element strontium. Strontium. So strontium's a group 2 element with a 2+ charge. Chlorine has a -1 charge, so it takes two -1 charges to balance that 2+ charge. So strontium chloride. So here we've got cobalt 2 chloride. So that Roman numeral 2 tells us that it's a 2+ on the cobalt. And we know chlorine is a group 7 halogen. So chlorine has a -1 charge. So two of them and the 2+. So the 2+ and then two of the 1 minuses cancel each other out. So cobalt 2 chloride. Here we've got barium, the element barium. So it is a 2+, it's in group 2. And then we've got arsenate. Now, arsenate is in our chart that we just looked at. Let me go back here. So arsenate is right here, and it has a -3 charge. So barium has a 2+, arsenate has a -3. So if we double the -3, that gives us -6 or -6. And then if we triple the +2, that gives us +6. So +6 and -6 together makes a neutral unit. So that is the formula unit for barium arsenate. Platinum arsenate. So platinum has a 2+ charge as well. It's number 78 in the middle of right in the middle of the table of contents. So it has a 2+ charge, and the arsenate still has the -3, so the same as the barium arsenate. And right here, we've got platinum 4 arsenate. So it takes, since it's got a 4+ charge, it takes 4 of the 3- charge to make 12 altogether. So it's 12+ and 12- to cause a neutral compound here. So platinum 4 arsenate is PT3 arsenate with so see how it's got the parentheses around the polyatomic ion and then the subscript on the outside. So altogether, this formula unit has these 3 atoms, and then you have to multiply everything in the parentheses by 4. So this would be 1 arsenic and 4 oxygen atoms. So that's 5 times 4 is 20. There's 23 atoms in the formula unit for platinum 4 arsenate. Okay, now the next ionic compound is copper 1 nitride. So this one's using the simple cations and simple anions. So copper 1 and nitrogen has a 3- charge. So it takes 3 of the copper atoms to neutralize the nitrogen. So copper, you just write the word copper and then put an IDE suffix on the root for nitrogen. So copper nitride, copper 1 nitride. Then we've got copper sulfite. So SO3 sulfite is on the chart before, and it has a 2 minus charge. And so the copper with the 2 plus and the sulfite with the 2 minus, it just takes one of each. And they did not use parentheses because there's only one of the sulfite ions here. Okay, so does that make a little bit more sense? Now, so they have the cation, then the anion, and they don't use any of those prefixes like the mono, di, tri, tetra. They didn't do any of those prefixes with these ionic compounds. So they just they skip all that because when you think about how they're all in that array, it doesn't really make sense to say tri and tetra and all that because there's so many of them. It's just kind of pointless to try to number all these different things. Thinking about the difference, why are the molecular compounds named differently than the ionic compounds? So these molecules, so here's chlorine dioxide, boron trifluoride, and tetraphosphorus nonasulfide. These molecules have so this one has 4 phosphorus and 9 sulfur atoms in it. But if you look over here at the ionic ones, if you say that that's sodium and that's chlorine, this chlorine is as equally bonded to this sodium right here as it is to this one over here, or this one down here, or its neighbor, and to the back and to the front and the side. It's as equally bound to each one of those as it is to this one and this one is. Okay, so let's review naming both kinds. We've got our molecular compounds on this page, and then we'll talk about practice naming ionic compounds on the next page. So remember, we have to use the prefixes when we're naming the covalent compounds, the molecular ones. And these are all non-metals. So that's how we can identify that these are the molecular compounds. Phosphorus pentachloride. So we write our P for phosphorus and Cl for chlorine, and penta means 5, so PCl5. Now, if you want to pause and write down your answers before we proceed, you feel welcome to do that. I'm going to go ahead and pull the paper back so that you can see what the answers are. So PCl5, iodine trichloride, I with 3 chlorines, dinitrogen, we have nitrogen 2, and then O with 0, or O for oxygen, 4 for tetra, 2 carbons and 4 bromines. And then carbon tetrachloride, carbon chlorine with 4 chlorines. All right, now doing the reverse, they tell us what the atoms are and the numbers, and then we have to write the names out. So 2 is di, so diiodine pentoxide. So if you haven't written all your names down, you can pause if you want to. I'm getting ready to click the paper away. So here we've got diiodine pentoxide, and that's really weird looking to write that because it still keeps the 2 I's, diiodine. So it'd be diodine, and that's just not even a word. So that I can see why they leave it, but it's just weird. And then pentoxide, tribromine octoxide, so 3 bromines and 8 oxygens. Diselenium diiodide, so there's the diiodide again, but it's got the IDE because it's at the end. And over here, you just write the full element, the whole element's name. The number 9 is dichlorine octoxide and carbon diselenide. So these are our ionic compounds that we're going to figure out the formulas for and write the names for. So first of all, we want to locate all of these ions on our chart. So some of them are simple cations and simple anions, and some of them are polyatomic ions. So here we have, I've written the cations in red and the anions in blue. So we do have to calculate how many of each one that we need to cancel, to neutralize the charge of the formula unit. So for number 11, we've got calcium and carbonate. So the carbonate ion has 2 minus and the calcium has 2 plus. So right away, they cancel each other out. So we don't have to have more than one of either one of them. The second one, we've got the ammonium ion. So remember, it's the only one that's on this chart that has a plus, that has a positive charge. So ammonium with the 1 plus, sulfate with the 2 minus. That minus is hiding over here. So we need 2 of these to cancel out the 2 minus. So we're going to need to keep these parentheses. So we have the NH4 inside the parenthesis, and then we're going to write a little 2 on the outside, and then we're going to have the sulfate ion, but we don't have to keep it in parentheses. We don't have to put it in parentheses because there's only one of them. Number 13, calcium chlorate. So calcium is in group 2. It has a 2 plus charge, and this chlorate ion right here, ClO3 with a -1 charge. So we need 2 of these to cancel out the 2 plus. So calcium with the we'll leave the parenthesis and write a 2 right there. Copper cyanide. So this one has a 1 plus and that has a 1 minus. So we can just get rid of the parentheses and have copper Cn. Now, potassium has a 1 plus, carbonate has a 2 minus. So we need 2 of these to cancel that out. Lead and sulfur here, we need, this has a 4 plus and that has a 2 minus. So we need 2 of these. So lead with a S and a subscript of 2. Now, aluminum oxide. So aluminum has 3 plus, oxygen has 2 minus. So we have to crisscross multiply here. We'll need 2 aluminum atoms and 3 oxygen atoms. So aluminum 2, O3. And the silver and the acetate. So the silver has the 1 plus, the acetate has the 1 minus, so 1 of each. So our answers should look like this. So moving on to number 19, if you want to pause and fill out your guesses and try to do it ahead of time, that's great. We're going to write down the names of what these things are. So again, we're going to identify where all these elements and polyatomic ions that we're going to be using are. So I think you know the names of the elements pretty well, so I didn't highlight them, but I did highlight the polyatomic ones that are down here because we haven't used them before today. So Ag is silver, and Cr2O7 is dichromate. So that's what it's called. It has a 2 minus charge. Iron phosphate, so we know where iron is. and phosphate PO4 with a 3- charge. Number 21 is copper sulfate. So copper is up here, and sulfate is down here, SO4 with a -2 charge. Iron fluoride, so iron and fluorine is the element. Lead nitrate, so nitrate is right here, and we know it has a -1 charge. So magnesium and bromine, and tin, and then SiO3 is silicate, SiO3 with a 2- charge. So we don't have to use all those prefixes. So this is a lot easier, but we do sometimes have to do the stock system. So like number 20, remember iron was one of those that has it can do multiple charges. So in order to figure out what Roman numeral we write down, phosphate is right here with a 3- charge. So they only put one iron here. And if we know that phosphate has a 3- charge, then iron has to have a 3+ charge. So we're going to put Fe and then parentheses and put a Roman numeral 3 and then phosphate. Now, number 21 is copper. It also can have multiple charges, so we have to do the stock system on it. Copper can have a +1 or a 2+ charge, and sulfate has a 2- charge. And they only put one, so that means it has to be a 2+ charge. So copper 2, Roman numeral 2, sulfate. Number 22 is iron, and fluorine has a -1 charge, and there's two of them. So we know iron has to have a 2+ charge. And then number 23, so number 23 and number 25 both, we have to calculate what the charge is, and we have to put a Roman numeral for the stock system for lead and tin. So nitrate has a -1 charge, but there's two of them. So a -2, so lead has to be a +2, Roman numeral 2. And then number 25, 10 can have a 2+ or a 4+. And silicate has a 2-, and there's only one of them. So that means that that tin atom has a 2+ charge. And then magnesium bromide, now skip that one, but both of these are elements group 2 and group 7. So magnesium always has a 2+, and bromine always has a 1-. So 2 and, well, we don't have to match up the charges on that one. So silver dichromate, iron with the Roman numeral 3 phosphate, copper with the Roman numeral 2 sulfate, and all these just like what we said. All right, let me know if you have any questions or if anything's not making sense to you. I think you should be all ready to take your quiz number 5. I've got a funny and a serious thing that I found that I wanted to put on here. So if you're a James Bond fan, Ionic bond, taken, not shared. And then for the serious thing, at church today, we talked about this verse, and with all the compounds and things that we've been talking about, how all the atoms are bound together. The Lord did all that, and without him, nothing would be able to hold together. There wouldn't have been anything created. It was just it's just beautiful to learn how intricate, and the more you learn about anything, the greater it is. your appreciation for our Creator, at how wonderful He made everything. So, anyway, I just hope that learning anything about science and things that the Lord has made for us, that gives you a blessing. So, anyway, that's all I have for this lesson. We've got one more section for chapter 3. So talk to y'all later. Bye.